So we were looking at maximum likelihood estimation for a two-state Markov chain, and notice that as the sample size increases, the maximum likelihood estimator of the diagonal components of the two-state Markov chain, the only two parameters, seem to be reaching some steady state in the estimator itself. And the likelihood, log likelihood function seems to be concentrating on that same point. And then you were supposed to think a bit about what it means if you model this as a Bernoulli experiment. And so the next main topic I will sort of briefly point out is random walks and random graphs in stage. So here, so we talked about two-state Markov chains. So the natural way to think about generalizing a Markov chain on a graph is the following. So you simply throw the states on the blackboard for now, and then you put these directed arrows representing where you can get to from where. And so that gives us immediately the following. So you have some state, you can get from here to here, there, here, and so on. So now you should start recalling the social network analysis module of Simon's, for example. So these could be users, web pages, whatever, and there's some activity. And typically you have to represent the state of the system as something that moves around between these states according to these out edges. Okay, so this could be embedded as part of a huge graph. So this is a directed graph or digraph. And when we put probabilities here, right? So let's say the so-called simple random walk on a directed graph, on a digraph, is this rule. So you look at every edge, every node, state, and look at all its out edges, and count the number, and if it's finite, then you just do 1 divided by the total number of out edges. Okay, so here it'll be 1/2, there are only 2 out edges. You would allow self loops. So this is, say, Hotel California. You can check out anytime, but you can never leave. You know about the song and the Eagles? It's one of my favorites. Okay, this is kind of not ideal when we have things like this. These are irreducible classes, which is one state. So if you go there, you're trapped there forever, which essentially complicates our stationary analysis. Okay, our stationary distribution analysis now will depend on where you start. Okay, so these are subtleties involved, and you really need a few weeks of really understanding this, because you have to get into the greatest common divisors of the shortest paths and all of this. But up to all these number theoretic fielding, you can do what it will end up doing for you. Yeah.
Sorry, can you have one path with half probability of staying and then one leaving?
Yeah, sure. You can do whatever. So yeah. So let's do one more here. So this guy stays here with probability half, and then with probability half, they send you to Las Vegas. Okay. Yeah. Something. Sure. This is fine. Let's say something like this. This is fine too. Right? So it's just that every node, the sum of the probabilities of the outgoing edges should sum to 1, because that becomes the row of the transition probability matrix with this state. Let's call this state 0, state 1, right? So if you fill this out, you'll have a transition probability matrix, right? 0, 1, 2, 3, 4, 5, 6 states. And if I fill for 0, 0 is going to have 1/4 on 1, 2, 3, and 5, right? 1, 2, 3, and 5. And it has probability 0 of drawing here. This is how you fill the whole thing out. Right? That's just going back to a transition probability matrix, whole P. So that's the connection between matrix and digraphs. So what I wanted to point out is something called a simple random walk on a digraph. So in this, it's called simple random walk because you always do this 1 divided by the total number of outages. That's why it's called simple, right? And this is what you guys did when we started doing the drunkard's walk yesterday or last week in 1D, right? So we had a lattice, so the guy starts here, or the girl. And then if we have going up and down with equal probability, half and half. So I'm going to call this state 1, this state 2, this state 3, this state 4, right? So we call this. So then from here, goes here with probability half, and back here with probability half, right? So if I have this, then remember, this is just a graph, right? So I'm just putting this because this is the usual way of thinking about the integers, which encode the places, this is the states, right? But so here is the implicit diagram. So it's just the same problem, okay? And this is a simple random walk in a 1D diagram. This is more general, but the ideas are the same, okay? Everything just carries over. You don't necessarily need a simple random walk. So this means you will have some other sequence of numbers that sum to 1. So it doesn't have to go to, in Google's PageRank, what's happening, it's just that, there may be more than one link going here. So although, so now I have to do 1, 2, 3, 4, 5, 3, 6, right? So I added 6 more. Or did I add 7? I don't know. You get the idea. So now you see there's more flow in this representation with every link, hyperlink, getting equal probability. It's a simple random walk on the hyperlink graph. But if you collapse this, so this, I don't know, this is another move you can do, then you will get the sum of 1/6 and 1/6 here. So it'll be 2/6. So there's more probability of going from here to here, right? This is in Google's PageRank. But just bear in mind that that's a completely. So now we have this nice connection between. So this is a simple random walk on a digraph, but then you can ask the question: should this digraph be deterministic and fixed for all time, right? What happens in the real world? The web pages go busted. People can't pay their GoDaddy bills. They lose their web page or domain name. So these nodes come pop in and out of existence, and new links are formed as the world evolves. So the underlying directed graph itself is evolving, right? So then you can have a page rank or a simple random walk on each instance of this evolving digraph. Now what you need is models of digraph itself, random. So this is the world of random graphs. So we have some of the world's best experts in random graphs in Uppsala's math department, right? Really. So that's another whole game. This is a really wide open problem, both pure math end and sort of applied data science pipeline ends. And then Mariama isn't here, but she was asking how she could use these kinds of graph representations of her simulation systems in molecular evolution. Remember, she studies these, whatever happens to molecules as they interact, and she can represent certain molecules and configurations in certain environments using these kinds of things. But then whether she's interested in a simple random walk or not, in that case, she actually has an evolving graph situation, right? Then you need to bring in these things, and I mentioned this as something you can explore. You search for Tegra. This is Apache Spark, so one of the latest time-evolving graph package that builds on top of GraphX and graph frames and other things. And Gaffer, I think it's so GCHQ, the British intelligence guys. They have a library called Gaffer, which overloads on Accumulo, right? So remember, these are other things besides the Hadoop ecosystem. Accumulo itself overloads on Hadoop, HDFS, Hadoop file system, which is basically recall as a open source version of Google file system GFS, right? And so Accumulo is basically like a metadata holding structure on top of HDFS that can be optimized for certain problems. So in the graph context, the guys, the British GCHQ guys, are essentially using Accumulo over HDFS to maintain buffers of terabytes of graphs, to keep track of system states. So there's a lot happening on the data science and engineering end as well. Of course, the mathematics is also like, yeah. So these are called random walks on random graphs, okay? And these random graphs are sometimes called random environments. So all of this, I'm not kidding, to get insights into this, into simpler models of this and building your mathematical intuition and modeling intuitions out, I hope these points will take us somewhere here. Sorry, what?
There's some F in the second.
Oh, yeah, thanks. Yeah, I don't know where that came from. Thanks.
Sorry,
yeah.
one quick question on the time evolving graphs. Do you have two probability or transition systems, one in the sort of cross-section and one in the time dimension?
Yeah, I mean, so I mean, this is very complicated, right, to get into, but remember, we cannot do any inference if we don't, so there's continuous time running, so these are all continuous time Markov chains, and I haven't told you about how to bring time, a continuous time. We only look at discrete time, but there is a way to add continuous time. And in fact, it's not that hard. The way you add continuous time is basically taking this transition probability matrix, okay? And then you need something, you have to convert this P into something called the generator Q. So this is called the generator of a continuous time Markov chain. So this is discrete time Markov chain, right? Discrete time Markov chain. But for continuous time Markov chain, you need Q. So there's a canonical way of going from P to Q if you're willing to make certain sacrifices in the mathematical assumptions, basically. So the way you basically do this, conceptually, it's very simple. I'm in some state 0, right? Okay, let's go back to our frogs on lily pads. Now, on each lily pad, these are heavy-duty lily pads, right? There is also an alarm clock that rings such that the time between its rings is an exponentially distributed random variable with rate parameter lambda sub I. So on lily pad 0, there is a clock, and its rate parameter is lambda 0, and it rings. So when the frog say it landed here, this is when we observe the frog. We don't know exactly when it landed, it's okay, because we're using exponential. Now, this alarm clock will ring according to this rate parameter, right, which is given with a PDF lambda naught e to the minus lambda naught t. So there will be some realization of that exponential, and then the alarm will ring. When the alarm rings, the frog panics and rolls the die. And it looks here to get the probabilities of the die, right? This is the discrete time. This is called the skeletal chain. So it'll roll the die and choose where to jump to. Once it jumps to another pad, let's say it jumped to 2. So this is another lily pad 2. So the frog is here. It's a prince frog, after being kissed or before being kissed, I don't remember. Okay, then it's also, there's another alarm clock here. And it has rate parameter lambda sub 2, right? It could be different. And that alarm clock will ring at its own rate. And when that rings, the frog will roll that little dice here with this many states and decide where it's going to jump to. That's how you couple, right? I don't want to get into the mechanics of it, but generator has its own conditions it needs to meet, and it essentially becomes a linear ordinary differential equation, basically. So let's kind of sweep that under the rug, because the heart of the problem is not in the continuous time, it's really in the discrete structure, usually, the harder part. Let's see, I forgot, what was your question again?
It was about evolving time.
So now when you have evolving time, time evolving graphs on which simple random walks are happening, well, let's first of all make sure that we can do inference on this. So we will make sure our probability models are not too complex, that don't allow inference. So for inference, the question is, what is our data going to be for this experiment, right? So I'm going to assume, let's drop down into Marina's world. So now these are actually road segments. So we take OpenStreetMap, right? So there's some intersection here, some, whatever roundabout and so on. So we break all of this into tiny fractions, and each one becomes a state, and we throw this here, right? That's our OpenStreetMap representation as a graph, as a diagram, with one ways and everything. Now, maybe my data is actually the cell phone GPS locations of, say, people that are giving me their data, okay, or whatever. like the open traffic API guys, right? You know, you don't know who they are, but you get some signals from them, so you know where they are. So you know the sequence of integer states they're visiting with continuous timestamps. That's the raw data. Are you guys with me? So now these are called, you know, spatio-temporal co-trajectories in sort of applied world, right? It makes sense. They're trajectories, they're because they co-occur, and they're over space, some representation of space, and over time. And for Marina's problem to be really explicit, she only has cell tower data. So we have to do some kind of Borman tessellation of space. And then these tessellations will actually have sets of OpenStreetMap in them. We won't know where they are, but the tessellations will tell us that the cell tower signal is there or whatever. So no matter how you break it into finitely many discrete states, you have co-trajectories, which are just like, for us, the dry wet chain is just a sequence of zeros and ones, right? And then what you have to do is, let's say, I don't know, this is some fancy world where the roads keep changing or whatever, then you need to give yourself enough time, right, to be able to infer the graph. And you cannot really infer the graph if the graph is changing at every instance of the person moving. I mean, it's, you know, it's too much, right? Where is the information going to come from? So this is reasonable. If the roadways, for the roadways, they only have 2 years of data anyway. There's going to be, you can just take the OpenStreetMap right now and just do it. It will be a static graph, no problem, should be reasonable for most things. But if it's like a website context or social media, and you're interested in how people friend and unfriend each other and the rates at which they do this these days, these will become important, because if you unfriend someone or unfollow someone in Twitter, you don't get their tweets, right? So what messages you get bombarded is a function of your choices you made in your own personal social media profile. So if that's evolving at some rate, we know that it is, then we need to make sure that we give ourselves some reasonable time. We have to investigate with the data and so on and say, okay, I give myself, you know, on average so many days or whatever, or so many events should happen, social media events. Right here, it could be whatever, some retweet is getting transmitted from this person to that person, and this person retweets them. You know, it'll be like some kind of simple random walk encoding of the transactions. Then, you know, for that part, maybe you can say there is this, you know, implied graph, because we know communications happen. That graph is there, so you can try and basically infer the transition probabilities in a non-parametric way, right? Because if a communication happened, you know that edge is there. But if a communication didn't happen, then it's just that maybe the edge is there, but nobody did that, right? And in Twitter, this is the case. Twitter follower networks are so huge because Trump has millions of followers, right? But lots and lots of those followers will not have responded by, say, retweeting one of Trump's tweets in that, say, 1 month or whatever we're observing, maybe a week. So then there are very sophisticated methods that I am not, you know, too good at, that you can bring in. Basically, you need the follower graph information that you can mine, which is a pretty intensive process. And then you can use the follower graph as a support graph, like that is where the transactions happen, the simple random walks, whatever happened. And then you have to bring in other methods, like you have to bring in Bayesian methods, and you may have, there's a prior probability on the follower graph that things will happen even without observing transactions. And then, you know, so all these bells and whistles you can add, but you probably have to do a PhD. All right, I kind of want to keep this. We've got 2 more notebooks, so let me not get too distracted. So here's just a quick. Oh yeah, so you're here. So this is for you. You know, I made this especially for you last night. She's doing population genetics, right? So yeah, so basically, yeah, I mean, this is the walk some of you guys already did in 2D. I'm just bringing a time component and increasing the number of steps you make, you know. And as you can see, I told you already that this is the primitive object that whose scaling limit becomes the Wiener process of Brownian motion. Okay, so and then this is just another little interact. See how tiny this is, a 3D walk. So you guys did some of the 3D walk. Look at this code. I purposely did it in the mean way, so you learn functions and stuff. But here is a very, very simple 3D walk. It's 4 lines of code. So this one's by the founder of Sage, William Stein. Okay, so it does this nice rendering in JMOL, as you can see. You can increase the number of samples, and you can also have multiple random walkers if you're a bit stubborn, just having an outer loop on top of it, and have each walker in a different color and things like this. But the maths for 3D Brownian motion is like non-trivial, right? So it's not you already hit open problems in pure maths, asking simple questions about 3D walks. This is a graph browser by Marshall Hampton. So it's just giving you a quick look into all the various random graphs and deterministic graphs that are already in Sage graph library. So I don't know, I think this is a grid graph in 2D. Let's try this. Balance tree, let's try a grid graph. Okay, yeah, so there's a lot. There's bull graph and circular graph, circular ladder graph, cube graph, degree sequence configuration model. This is actually what I was using. Degree sequence configuration is what my null model was for my Twitter random graph story. Oh boy, there's a lot, right? There's also empty graph, thank God. Grid graph, let's do grid 2D graph, just because it's easy to visualize it. So here you go. There's a grid 2D graph. So you can choose the parameters, you can specify the tuples. And this is just to show that these graphs exist, but of course you can call all kinds of methods on it. So it's a very rich place where you can start playing with your sort of intuitions of how to go about for your particular problem. Yeah, and this is essentially the, if you're interested, let me know. I have a full Sage worksheet going through the entire programming guide of this whole library, every single function, at least last year, I think. I mean, that's how I study. Like, if I study something, I just kind of study slowly. Yeah, and I don't remember stupid things like this morning, the second derivative, the maximum, the likelihood should be negative, right? So, overcomplicated. So anyway, it's okay to make mistakes as long as you come back. Okay, so now let's move into notebook 11. And we have only one more. So this, I guess, is I've kind of been talking about limits and convergence a bit loosely, so I'll slightly tighten the belt on this. Because you need to have a good understanding of what limits and convergence of random variables are to really understand properties of an estimator. So here is the big picture, so the outline rather. So we'll first look into limits, and initially we'll look at limits of sequences of random variables. And then, so let me come back here. We look at limits of sequences of random variables, limits of functions, and then, limits of real numbers, limits of functions, and then limits of sequences of random variables. Then we will get into these notions called convergence and distribution and convergence and probability. There are two specific notions of how random variables, a sequence of random variables, converge to another random variable. There are many more notions of convergence, but this is the two most basic ones we need to appreciate these laws. There are several limit laws in statistics. In particular, we look at weak law of large numbers and the central limit theorem. And those are the two main ideas that help us with point estimation and set estimation and justify these concepts. And the big picture is something like this. So we'll see how quickly we can cover this in 1 hour and 15 minutes. Yeah, so basically point estimation, I told you, we're just hunting for the single best guess, and set estimation is some kind of a random set that tries to capture the single point we are after. And this is the maximum likelihood estimate of finitely many parameters setting. We do what's called parametric estimation, because the number of parameters is finite, maybe several million, like in neural networks, but it's still finite, okay? And then set estimation in confidence, examples of confidence intervals. And here we will need the central limit theorem to justify this theory. And this is also parametric, right? Finite dimensional parameter spaces. But the point we're hunting lives in a finite dimensional usually real space. And then the other one is non-parametric. So here we have infinitely many parameters, uncountably infinitely many parameters. And this is sort of coming up. And I don't think we have, we'll get to this part, right? How to use a lot of this in more concrete examples. So what are limits? So this last hour we described Markov chains, and we saw that the state, you know, the state probability vector Pn as n goes to infinity approaches some fixed point, some stationary point, which we call S, bold S, right? So and then we also noted that Pn only converges to a strictly positive vector if P is a regular transition matrix, right? So it means all, you know, all the rows sum to 1, and then you can get from any state to any state, right? Otherwise, yeah, it becomes more complicated. So the week before we also saw this, right? We saw that the class before that, we saw the likelihood function has this nice property. So as n goes to infinity, the maximum likelihood estimator of the Bernoulli random variable converts to the true parameter theta star, right? If the model really came from it. So we've already seen limits of random variables by kind of hiding the details under the hood. So now we're going to basically open the hood. So here's just a simulation of the likelihood function for the Bernoulli process. Here the process just means the maximum likelihood estimator for every n as n increases. Okay. So you can see how it's really concentrating around 0.3, right? That was our secret theta. So what does it really mean? Because now for each instance, each sample size n, as it goes from 1 to 1,000, we have a sequence of random variables, right? Which is now theta sub 1 hat, theta sub 2 hat. You see? Now all the notation really helps, right? This was the sample size. So this is converging in some sense, I don't know what sense, to the true theta, at least in the simulation where we control this and actually show that this works. This for us was 0.3 because we rigged it like that. So yeah, this homing in is how do we say this is a nice property? And of course, that's a nice property from a decision theoretic point of view, because what does this mean? This means as the amount of information approaches infinity, as n goes to infinity, we want our estimator to approach, in some sense, the truth. Right? That's a very reasonable assumption. I mean, if you give me an estimator that doesn't even do this, and this is not even saying the model is right for the problem, it's like even in your la-la land in your head called mathematics, if this doesn't hold, you have a really bad estimator, right? So this is usually considered to be the minimal property an estimator should satisfy, and this is called asymptotic consistency. Okay, so to really understand this, we need to really understand what this means, what this convergence notion really means, instead of just animating it. Yeah, so let's just hit shift enter on that one. There's a lot of code will sort of just to feel us conceptually, but you should be able to understand all of it pretty much. Just Python you already know. So this is our Bernoulli theta running means function. And this is the actual interact from before. So in this one, this one we just saw that if I take, this is very, very important. So now not only is, this means for different samples, so in say different universes, you do this experiment, repeated it, or in the same universe, you just flip the same coin multiple times. And each one you looked at it, we also noticed that the sample mean converges to the true parameter theta star. Okay, so here is the thing with standard Cauchy running means, right? So if you did this for the Bernoulli running means, right, we have this nice convergence, and but it doesn't work for Oh, something really crazy happened. Oh, look at this. So one guy went all the way up. What are you guys? Okay, so this is, you know, it's my timestamp, whatever the initial seed is. So you see, this will never settle down, as I said. It just keeps jumping like random everywhere. And this is because the expectation doesn't exist for the Cauchy. So all this asymptotic theory is, you know, some of this will not hold when your underlying random variables, you know, don't satisfy certain properties that the theorem expects them to satisfy. Okay, so that's the main point with a concrete Cauchy check. Okay, so yeah, there's a bunch of typos here, but so let's look at limits of sequences of real numbers, right? A sequence of real numbers x1, x2, x3, dot, dot, dot. We usually notate it like this. You know, we usually put a set around it and say I goes from 1 to infinity, or a sequence symbol or parentheses around it. That's basically a sequence of real numbers. And we say it converges to the limit a. What does this mean? So this is like LaTeX hell between like Jupiter and the rest of the world. Okay, so this is how you notate it. So you say the limit of xi as I goes to infinity equals a, right? Because it's converging to some real number a. So what does this mean? This means if for every natural number m you give me, right? So 0, 1, 2, 3, and so on. Every natural number m you give me, I should be able to produce a natural number, capital N sub m. I'm allowed to produce this number n sub m based on the m you give me. Okay. So this such that for every natural number j bigger than or equal to this n sub m I'll produce, the absolute value between xj and a is less than or equal to 1 over m. So this is what it means to be converging in the reals, right? So you give me any m, so m could be 800 billion. So I need to find the number n sub m that such that every other number in the sequence xj greater than this n sub m will be 1 over whatever billion you want within a. Okay, is that clear? Yeah, it's like a, yeah. So if that's the case, that means I have a mechanism to show that all subsequent numbers will be arbitrarily close to a. That's basically what formalism here is. And look, the beauty is very, very important, you know, pay attention that there is no need for bringing reals or anything here yet, right? I mean, okay, a is real and all this, but this whole mechanism is just natural number game, right? Give me an n, I give you an m. So yeah, what is the saying? That's what I basically explained. So let's look at a trivial example. So let's look at this. My favorite number is 17. So let's look at xi being the sequence 17, 17, 17, 17, 17, 17. So clearly the limit as I goes to infinity of xi is 17. So that's, so but if you do this formally, so for every m you give me, I can take n sub m to be just 1. No matter what m you give me, I'll just say my nm is 1. Oh, then yeah, for all j greater than or equal to 1, xj minus 17 is 0. It's always less than any 1 over m that you give me. So that's an easy peasy one, right? And this is the symbol for all, or for every in mathematics, this weird inverted A looking thing. What about this sequence, xi, where we have slightly more interesting pattern now, 1 over 1, 1 over 2, 1 over 3. In general, xi is 1 over I. So, I mean, this thing is really like going close to 0, right? So, intuitively, it seems fine. So, let's say I guess that limit as I goes to infinity of xi or 1 over I is 0. Then I need to play this game, right? So, for every m in m, what should nm be? Okay. So in this case, you can just take nm to be m itself. So you give me an m, I will give you back the m. And then for every j bigger than or equal to the m, you give me xj minus 0 is less than or equal to 1 over m minus 0, which is 1 over m. So again, this is a little more interesting. So it depends on the m you give me, but it's the same thing you give me, rather than the one that I give you all the time as in the 17 case. So you can kind of play with this. This is another example. You can sort of. So here we have 1 over I to the p is my sequence, and this also goes to 0 provided p is greater than 0, and you can play exactly the same game. Okay, and this is just like kind of a crash course in like data analysis, right? So we can look at what's happening. Just plotting this. This is just it's really hugging 0 so fast, so you're not seeing it. It's just crash landing on So we can make this. Okay, that's pretty. 30. I thought I put 3. Oh, that's What is p? What did I set p to be? Oh, p is 1. Okay, that's So anyway, graphs are dubious. Okay, then there we go. This. So now when p is 1, what's p here?
You set p in the. It subs p equals
1 here, but
but for I equals 0, you take 1 divided by 0.
That's the problem. Yeah, thanks, Tom. I'm like, oh, thank you very, 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 very much. Okay, so that's what now? Okay, that's too close. All right. Yay! Yeah, that was my problem. I was like, oh, what's going on? I forgot 1 over. Yeah, good. So yeah, here I'm just taking p to be 1 again and just playing the same game, right? So now now I'm interested in the limit as I goes to infinity of 1 over I to the power of 1 over I, which will be 1, which is another sequence, right? So yeah, for all of these, you can actually sit down and work out m and n sub m and everything, and this will take a little time. And it's normally what I did homeworks like this in Minnesota in 1996, I think, second year analysis. When do you guys do this kind of stuff now here? Is this like just second semester? Yeah. Using natural numbers or rationals, not epsilon delta stuff. Explicit construction, right? Rather than I would guess somewhere in high school. Okay, that's good. So this is all high school maths.
You do the epsilon delta stuff in the first semester.
Okay. Good. So okay, back to the real stuff. I don't know why I put that there. Back to the real stuff. Oh yeah, limits of functions, because that was just some excursions on images, right? So now, so what we want is, we're not just interested in limits of sequences of real numbers converging to a real number, but we're interested in limits of functions now, right? So what does that mean? So you have a function f of x going from R to R, say, and it has a limit L, which is also a real number, let's say. But now, this limit L is actually in this way. So as x approaches A, in the usual sense, so you have a sequence x1, x2, x3 approaching A in the previous sense. Now I'm looking at the image sequence, right? So that's the main idea. So so let's just make a picture of this. And this is kind of what we were talking about. Thilo was here earlier about left continuity and right limits. All so continuity overloads on this notion of convergence of limits of functions. So now what we were seeing before is there is a sequence of xi's. And they're somehow like this. They go to A. And that's, so we say limit as I goes to infinity of xi equals A. That's what we just saw the definition for. Now we simply abstract this by saying x goes to A, okay, according to some sequence. And in fact, yeah, for every sequence in some sense. And then we are looking at what is the limit of f of x, right, as x goes to A. So this is our new notion. So that means we just have to look at, let's say there's a function like this. So I have to look at this image. Where is this? Here. This guy is here, and so on. So there's going to be, let's get the last guy here. So there's going to be some interesting thing, right? So it goes from here to here, and then look, it jumps above, whatever, and comes down. It can spiral around and whatever. So in the end, it should approach this, right? So we're now talking about this sequence upstairs. Yeah, so in English you say limit of f of x as x approaches A is L, provided f of x is arbitrarily close to L for every value of x that is sufficiently close to but not necessarily equal to A. So this is how we get away with those jumps, right? So I'm not really worried about what f of A itself is. That may not exist, or whatever, or it may be infinity, who knows, it could be something I can't really define. But I'm really interested in everything else downstairs approaching A, and then what happens to the image f. Okay, so that's how this is defined. So for example, consider f of x is 1 plus x, the power of 1 over x. This is our famous E. So as x approaches 0, this f of x is actually the E, familiar E, right? 2.7, blah, blah, blah. Even though f of 0 is undefined, right? Because 1 to the power of 1 over 0 is undefined, because 1 over 0, you're smiling. I mean, I want to caveat this. Okay, let's just implement this. So if we substitute in x equals 0 into this expression, so it will give us an error saying division by 0 error, right? Which is, because it basically 1 over 0 is an error, right? It's not just infinity. But if you're really, really careful about what's really going on downstairs and what you want to use the arithmetic for and all of this, I wanted to put this plugin. So if you're interested in the art of dividing by 0, talk to Professor Warwick Tucker. He's in the math department. So in fact, he gave a talk called The Art of Dividing by 0 when I was a PhD student in Cornell. He was a postdoc. And I always went to talks where there was free food, like pizzas. At Cornell, you can find free food like morning and evening. So I only cooked like 2 meals a whole week for years before I met my wife, So anyway, I went to lots and lots of seminars, which is great. And Warwick gave one of these seminars on applied math. Bill Steers Club with a lot of pizza and soda and fruits. So one of the talks was all out of dividing by 0, and I really loved all of this. So I did my sort of dissertation, although he left and he wasn't my advisor or anything, but I did a lot of mathematical statistics using set-valued methods. Yeah, so anyway, just division by 0 is also possible. Here is our little plots to look at this. X plus 1 to the power of 1 over x at different scales this time. So, yeah, so this is how it looks. So because I'm not plotting the actual value at 0, I'm able to get away with. So it's converging somewhere, right? And that thing is actually a well-defined thing, although the actual image at 0 is under. So that's limits of quick thing on functions. And so now limits of sequences of random variables is another beast completely, right? Because remember, these xi's are random. That means, every time you perform the experiment, it will take different values, right? Unlike this deterministic sequence, because every time x1 is always x1, right? There's nothing going on. But capital X1, it doesn't land in one place. Capital X1 takes, it has a density if it's continuous or something, right? So it can take one of many values. So now we have to conceive of notions of convergence of random variables converging to other random variables. That's this idea. So what is really limit as I goes to infinity of capital Xi equals capital X mean in some sensible way. So capital X is called a limiting random variable. So you don't do this in first year, right? This is usually in a probability course. This is graduate level or advanced undergrad level?
Well, it's not in the first probability course. I would say advanced level.
Okay, that's good. So we're jumping from high school to 14 months. But the ideas are basically not that complicated, I think. So yeah, here what I'm doing. So let us look at this simple thing. So let's understand this real number, x1, as a point mass random variable, right? We talked about this last time someone asked. So I said, well, we can put the distribution function for this guy as a point mass thing. So there's no worries. So we can, oops. Interesting. Okay, sorry. So if I look at it as a mass function, the number 2, say some number called theta is 2, it's exactly here, puts all the mass here, which means what? It's 0 everywhere, except there's a hole punched here, and then there's a filled hole here, right? And then so this is why when we write our own functions, we can be explicitly precise about what we mean by function, right? And then this is the distribution function, so it's 0 up to the point 0, and then it plucks a hole, and then puts that hole, fills it here, and it's always 1. So that's how we represent a deterministic number as a random variable. It's called a point mass random variable. So that's the mass function and the distribution function for it. It's 0 if x is not theta, and its parameter is the number itself, right? And that's basically how you think of it. So if we had some sequence of theta i's, right? So these are real numbers converging to theta, we can just think of this as just a sequence of random variables xi with point mass theta I converging to this, right? So it'll be no biggie. So it'll be like this. This guy, let's say this is 1, like that, and this guy is this guy. So they're all going, and they're all converging to this guy. So that's nothing. It's exactly the same conceptually. We just think of it in terms of distribution functions. But what about more generally, right? So this is just a little plot showing this, just the point masses converging to something. Now let's say we want to talk about this more generally. So here's our familiar beast, finally introduced, the Gaussian mu sigma square random variable, or the normal mu sigma square random variable. So this is one of our basic location scale family, the first one you're seeing. So this is called the location parameter, and sigma square is called the scale parameter, right? Because mu controls the center where the mass is, the mean is, the population mean. And this parameter is the population variance. So with these two, we specify Gaussian random variable. So mu can be any real number, but sigma square is, of course, greater than 0. So here is its density, probability density function, right? So it's basically taking x minus mu and squaring it. So, right, so it's putting, it's just having a little cup here, centered at mu, quadratic cup centered at mu, whatever that's called, parabola. And then we scale it by 2 sigma square, so we control how wide or this cup is. And then we put a negative sign, so we invert the cup, right? And then we exponentiate it. So So that's what's going on here, right? So and then we do this normalization to make sure it integrates to 1. So you sort of tell the construction by Gauss's, right? Yeah, so then we basically can play around with this interact. It should tell you, this is stuff you know, but let's say we make sigma to be 10. So that's getting spread out a lot. And if we make sigma to be 0.001, it's concentrating it like crazy, right? So also called direct delta density because it's like the spike. So engineers use this a lot as well, with the one with sigma almost 0. Okay, and you can change the location, of course, so where it's centered changes. So that's our basic Gaussian random variable. Now the question we really want to understand is more like, consider a sequence x1, x2, dot, 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 where x1 is normal 0, 1, so the center is always 0. x2 is 1 over 2, standard variance. x3 has variance 1 over 3, and so on. And in general, xi has variance 1 over I, right? So we take our real sequence, which we know converges to 0, and stick that as the parameter, the scale parameter, the variance parameter. And the question is, where is this xi's going? In what sense are they going where, right? So that's the thing we want to first understand. So here's just a normal curve animation looping. So as sigma being 1 over I increases from 1 through 25, we just are observing a concentration of the PDS. So the corresponding xi's probability density functions are spiking at 0. So a good guess is that this is going to lead to a point mass random variable at 0, right? You guys agree? I mean, all, was because my variance is approaching 0. It's centered at 0, so it's going to have like an infinite peak. The density will have an infinite peak. So if I integrate the density, in the limit, I will get all the mass at 0. So which is this point mass random variable at 0, right? Okay, you with me? So so and if you look at it as CDFs, what's happening? The CDFs are like this, and they're concentrating more and more like this, right? The distribution functions are. So this is just showing the PDFs. Okay, so that's our guess. So let's try to make sense of this. To talk about this, we need to refine our notions of convergence when we're dealing with random variables. Because for any I, however large, the probability that xi equals 0 is 0. This is crucial, right? Because this is a continuous random variable. For a continuous random variable, if I give you any real number and ask what's the probability that this random variable takes this real number, it'll always be 0. You agree? Because for a PDF, what are we doing? I mean, we always integrate, the probability is specified by the integral, but the integral over an interval that has 0 width is 0, because there's no floor space to integrate. Right? So then we have this problem, right, of how do you deal with this basic issue. So the simplest solution is called convergence and distribution. Okay. So let x1, this should be x1. Let x1 through x1, x2, and so on be random variables, and they are converging to, in distribution, we say, to some other random variable called x, the limiting random variable, right? If we consider this setup, so if for any real number t, right, at which the distribution function f of the limiting random variable x, right, so f is the distribution function of the limiting random variable. If for any real number t at which the limiting random variable's distribution is continuous, which means what? Which means this, right? F sub I of t equals f of t as I goes to infinity. Okay? So then we can say that the sequence of random variables xi converges to x in distribution, and write that xi arrow with a d on top to x. So this is how you notate convergence and distribution. So we are basically saying that, so this is a point, right, t, and at this point, right, the limiting random variable, which is this the distribution function of the limiting random variable, which is my f, right? This guy is f. So f of t is fine, right? I mean, f of t exists. There is no issue with this. F is continuous here. So then the question is, I have to look at this sequence, capital F of I at t. What is f of I at t doing? So that's these things, right? So this is really converging to downstairs. So no issue. So that we basically see, this is the thing about mathematics. And so we just remove the problem point and we say this is the definition. So I don't know. This is what mathematicians do for a living, right? So you see, there's no need to worry about that point because the distribution function is not continuous there. The limiting distribution function is not continuous at the problem point, right, where the jump happens. So for every point where it's continuous, I can do this, and that's the idea. You can read this, I'm just sort of recalling what does this really mean for the full probability model and Kolmogorov's capital omegas under the hood and everything, but it's the same thing. So yeah, of course, when you understand this, you should really understand what's going on with calling the definitions of probability and everything. Okay, so now that's essentially convergence of distribution to the point mass random variable x for the Gaussians, where this variance is crashing to 0. Is that clear? Okay. So here's just a little picture of a sequence of converging normal distributions, and I'm just showing again this sort of PDF picture. Yeah, so this is the point I mentioned already. So there's nothing wrong because we basically removed the problem point, right? The distribution function is not continuous at 0. So it's not part of the definition that needs to be satisfied by the limit as I goes to infinity of fi of t equaling f of t, because it's only for every t where f is continuous. Okay, so that's basically the idea. So that's our limiting random variable for this problem. Now, this other notion is more subtle. It's called convergence and probability. So now what we're saying is a little different. So we're saying let xi, this is annoying. Sorry about this. So let x1, x2, and so on be a sequence of random variables. And let x be the limiting random variable or some other random variable. Then capital Fi is the distribution function of xi, and capital F is the distribution function for x. Now, if for any real number epsilon greater than 0, okay, if the following happens, okay, so now this is a different statement. So we're saying as I goes to infinity, the probability that the absolute value of xi being away from the x, right, this is being more than epsilon, the probability that the absolute deviation of xi being away from x more than epsilon is 0, then we say that the sequence converges to x in probability and write xi arrow super p x. So this is a different notion, it's stronger, right? So what does this really mean, the probability of the absolute xi minus x? It means, this really means this. It means the limit as I goes to infinity of the probability of the set of all omega such that the mapping absolute value of xi of omega minus x of omega being greater than epsilon is 0. That means, the probability space is fixed for all the xi's. This is a common misconception. The capital omega is there, and the signal algebra is there, and all of that stuff is there. Now we have not just one measurable map, one random variable. We have a sequence of xi's, right? They're all mapping to the reals, the same space, let's say. Then what we're interested in is this event, the set of all omega such that, the difference between xi and x being more than epsilon, right? For any positive tiny, possibly very tiny epsilon. That probability should go to 0. That's the... So informally, we are saying x is a limit in probability if by going far enough into the sequence xi, we can ensure that the mappings xi of omega and x of omega will be arbitrarily close to each other on the real line for all omega in omega. I don't know. It's easy to understand it on the explicit examples. Oh, I forgot to bring the double pendulum. Oh. Oh well, anyway. Yeah, so then this is an important note. Convergent distribution is implied by convergence and probability. So convergence probability is much stronger than convergence. Okay. Yeah, this is maybe that's, I don't know why there's two of them. Oh right, so yeah, you think like this now, right? So you would so if you have a limiting random variable, then you would actually try and get an idea of the probability statement. You can look at the probability integral of this density function. So it helps to think like this. So what this basically means is, if this sequence of random variables xi are same one of Gaussians is converging to point mass and probability, what we mean is if I put a tiny little epsilon interval around 0, right? So if I put a tiny little epsilon interval around 0, the question is, yeah, so the question is this. So let's look at it in PDFs, probability density functions. So this is 0. And so say this is some xi. And after a whole bunch of, so let's say this is some xj, which is much bigger than, much bigger than I. So this keeps converging, right? And it spikes like a lot. And remember the point mass random variable has all the action here, right? Everything is at this point. So what this says is, if I look at some little interval epsilon, however tiny, and then I find the set of all places where basically I have to find out where this xj is not, so outside this epsilon interval, if I integrate the PDF outside this epsilon interval, that's going to be going to 0. That's all this is saying. You see? Confused? All right, so how do I do this? Yeah, so basically, I have to integrate the density function, so the ith density function of x. Right, I'm not going to put the parameters. So this is for the ith guy. If I integrate it from minus infinity to epsilon minus epsilon, and then I also integrate it from plus epsilon to infinity. Right. This is where they differ by more than epsilon, right? Because for the limiting guy, everything is here, so I don't have to do a. If the limiting guy also has a density, then I have to bring in that density and take absolute differences and stuff. So everything kind of squeezes outside. I mean, what's outside the epsilon interval around 0 vanishes. That's what. If that happens, then we have convergence and probability. Okay. Yeah, I think that's what's being explained here. So now this gives us an opportunity to talk about some basic limit laws in statistics, right? So this is called the law of large numbers and the central limit theorem. So, and we're looking at something called the weak law of large numbers. Because, yeah. So what's the basic idea here? So if I have x1, x2, so on, that are IID x1, so that means I have a sequence of random variables that are independent and identically distributed. And if the expectation of x1 exists, so everything but Cauchy in the examples we've seen, then the sample mean converges in probability to the expectation of the random variable. So that's not bad. That's what we saw in the Bernoulli, for example, right? And so, but it says for any random variable, the sample mean converges in probability to the expectation, the population mean. Okay, so it's, and then of course the sample mean is a random variable. Right? And this is a point mass thingy, right? Expectation of x1 is a number, real number, for any random variable. So it's exactly what we did, except now this this sample mean can have different, it may not just be Gaussian, it may be more complicated. And that's what I'm sort of explaining here. So it just means this convergence probability, and this is a way to properly understand this Bernoulli process of running means that we saw. And also the Cauchy, when it wasn't converging, that's again, doesn't violate the theorem because we need the expectation to exist for this to work. Okay, so that's that. Okay, so yeah, I mean, I think so that was our magic data, right? So this is just one sample. You can change the seed. So if you have multiple samples of this, so the real thought experiment you want is that there's like billions of samples doing this, and then you can construct a histogram or actually a PDF for each sample size, and that's the PDF of the xi, x sub n, x sub I superbar population running mean, and that's going to just spike out here, just like the point, it converges to the point mass at 0.3. Well, how much time was that? So that's well, let's go 5 more minutes to finish that. This is the fastest download. You kind of get the idea, right? So it's not intuitively, it's not very complicated. Just need more time to get into it. So now this is very, very important. This theorem is the second most important one. So this placental limit theorem. Here what we have is a sequence of independent and identically distributed random variables. And then you suppose that the expectation and the variance both exist. So the population variance and the population mean have to exist. So it's stricter conditions on what it can be. Then the sample mean converges in distribution to this random variable x. And elegantly, we even have the form for the random variable x, right? So the random variable x is actually normally distributed. Sorry, the random variable, the limiting random variable is normally distributed. That's what the statement says. It's a normal distribution whose mean is the expectation, okay? And its variance is the variance of the random variable divided by n. See, now everything is packaged together. That's why I set up the explanations of convergence and probability and convergent distribution in this way. So again, this variance decreases, like, inversely linearly to the sample size because of this division by n. So this normal squeezes around the population's expectation as the sample size increases. So this is kind of powerful, okay? It has these limitations, but if we have both the first and second moments, then, or the variance and this, then we basically are in business. So we actually have explicit distribution, limiting distribution for the sample mean. And this is all like if you're more into engineering and stuff, usually Z is reserved for the standard normal where the mean is 0 and variance and 1, and then you can re-express all of that in terms of Zn, but we don't really need to get into this. So, yeah. So sample mean convergence and distribution. Yeah, here's just some examples. PyLab interact. So yeah, if you sort of play around, this is what we've been seeing before. If I increase the sample size, and so this is so these are the number of samples that are being replicated, and so you basically have to find the right balance in the number of bins and stuff. But basically, you will see that this convergence has this nice normal shape, and that's what we've been seeing in all our simulations before. But the theorem is quite nice. It actually gives you explicitly the form itself as n gets large enough. And usually, n doesn't have to be too large for it to be approximately good. Okay. Yeah. I guess the point with the Bernoulli thing is that although the xi's themselves are not normally distributed or even continuous, the sample mean of this just 0, 1, the Bernoulli, is normally distributed. Right? And that's somewhat deep. If you get into the actual proof done by the Bernoulli weak law of large numbers, it's a lot of combinatorics under the hood, because the actual thing is really elegant, right? You have, yeah. So basically you have zeros and ones, so you can encode a right turn or getting a heads as 1, 0, and a left turn as getting 0, 1, right? So you can, this is basically 1, 1, so this is when tail head or head tail. So you actually have this random walk on this lattice path. This is actually one sample, one sequence of zeros and ones. And then all this combinatorics comes in. You have to count the number of paths that reach here, and it's very elegant. You can have a combinatorial proof of this. And it's the original proofs are combinatorial. Okay, so of course for standard Cauchy this won't work. And this one's just another interact for exponentials, I think. So when we do this and have some number of simulations, once again we'll see for exponential, if we choose the right bins and so on, it'll be again normal distribution for the sample mean. Okay, there's some U-tries later, getting into a bit more places where I got stuck, and I wish someone told me type stuff on various things. So you want to use this function called sample. So it samples 10 elements from it at random. So sample is, so if you have a big collection of numbers and you want to sample from it with or without replacement, these are very nice built-in functions that are highly optimized. And in fact, in the last few minutes, we will try to revisit these functions. So each call to a sample will select unique elements in the list. Means that it will not select the element at any particular position in the list more than once. So it's, but if there are duplicate elements in the list, then you may well get any of the repeated elements. So it's sampling without replacement. So it basically gives you permutations. Is that right? I always get this confused. Yeah. Yeah, I mean, basically for resampling, there are two things. It depends on the package. But so if you have n elements, what is the idea of a permutation? You have n elements in order, right? And then I'm interested in every possible ordering of those n elements. So I can have the first one as it is, or say for the first one, I can take any one of the n guys and say this is my first one for this new thing I'm going to create in order. And then I can take any one of the remaining n minus 1 guys as my second one, and so on, right? So that's why there is n times n minus 1 times n minus 2, so-called factorial, and factorial possible permutations or orderings of a sequence of distinct elements, right? So that's one main resampling strategy we will be using. The other main one is sampling with replacement. So I have things in a thing, I just roll it around and pick and look at it, or keep it, or note it and put it back, roll things around and do it. That's called sampling with replacement. So we need to, so depending on, those are important inputs for our null distributions downstairs. Okay, permutation, just look at the sample, shuffle, and choice are the different options. Now on to our last notebook. So we'll go till 3:15. So this is now non-parametric estimation and testing, and this is like modern statistics, kicking in like 1940s and beyond. So the topics are non-parametric estimation, the so-called fundamental theorem of statistics called the Glivenko-Cantelli lemma, Cantelli theorem, and then there's the most fundamental inequality in statistics called the Dvoretzky-Kuiper-Wolfowitz inequality. And then I'll just give you a tiny glimpse into hypothesis testing and a little bit into permutation testing, okay? And I don't know, for time permits, I was going to do a live permutation test on the full data. Let's see how far we go. So this is the big picture again. We are not going to be able to get into actual applications of more interesting thingies, but that's okay. We're about to see these two, so non-parametric point estimation and non-parametric set estimation. So this is our basic models, right? So we've seen these parametric models, Bernoulli theta, where theta is in the unit interval, exponential lambda, where lambda is in the non-negative reals, and normal mu sigma, where mu is any real number and sigma is in the positive reals. Sorry, this is also positive reals. So in all these cases, the parameter spaces can be seen as finite dimensional. Okay, this is something Marina was confused about the first time I mentioned it. All I'm saying is theta is in the unit interval. The unit interval is part of the line. So it's a subset of R1, right? Subset of real line. So this 1 is finite is the point. And the same way, lambda is in 0, infinity, right? It's also a subset of the entire real line. So again, 1 is finite because it's R to the 1. Real line in one dimension. It's all about the same, right? So then here, for the normal random variable, mu is in R1 and sigma is in R1 also. So jointly, the ordered pair mu comma sigma, the two unknown parameters, are in subset of R2, right, in the plane. See? So that's all I mean, you know, for the normal random variable, the unknown parameter mu can be any value in the real line, and the unknown parameter sigma can be any value here, right? So this entire part of the plane is the parameter space for the normal, and this is two-dimensional, right? It's R cross, it's a subset of R cross R, right? So that's also finite dimensional. And I'm not kidding, you know, neural networks, these are finite dimensional parameter estimation problems, right? Neural networks have million parameters, or 10 million, 100 million, I don't know. These guys and the Chinese and the Americans are fighting now. The French guys got in the game now, right? You saw the latest thing by Satya Nadella. They're helping France with their artificial intelligence. It's a neat talk, actually. There's a lot of, I mean, actually, Ecole Polytechnique, which I used to visit for the last 6 years, oh, actually, a lot longer, has evolved so much. Now they have these huge tech campuses. This is the school that Napoleon Bonaparte started to conquer the world, right? Called Polytechnique because he needed many techniques to wage war, right? It's a great school, actually. So anyway, it's full of these high-tech campuses now, and Microsoft Research's CEO just announced that they have this collaboration. So it's just good. I think more and more countries should get in the game of AI, and so when you have lots and lots of server farms, lots and lots of data, get a lot of people, you know, trapped into your data strategy, then your dimensions of the neural networks and deep networks are going to keep growing, right? But it'll still always remain finite dimensional. So for parametric experiments, we can use the maximum likelihood principle and estimate the parameters using the MLE, maximum likelihood estimator. But what do we do for non-parametric estimation? First of all, the non-parametric estimation problem is basically, I'm not making any compromise. I say, I don't know what the distribution function is. I want it to be, you know, arbitrary. I mean, give me the unknown distribution function from the set of all possible distribution functions. That's the change of the paradigm, right? So there's some observations from some unknown process, right? I'm doing the sorted observation. Maybe they'll land in different places if it's IID. So now I want to take this thing and simply reconstruct the unknown density F star. So this is the model. The simplest non-parametric product experiment is x1 through xn is IID F star. And F star is an element of the set of all possible distribution functions, which is uncountably infinitely many dimensions. So then we want to produce a point estimate for F star. And this point estimate is what we call F sub n hat, right? So now F star, since it's allowed to be any distribution function, we have this infinite dimensional setting. And this is just two distribution functions in the set of all. I can have jumps, everything is fine, right? I can have part continuous, part with jumps. As long as it's left continuous with right limits, I'm good. So that's the game. And the way we do this, we already saw this as one of our main statistics. It's called the empirical distribution function. So the idea is that the empirical distribution function F sub n hat, right, is going to be our single best guess for the unknown distribution function itself. Okay, so that's where we're going with this idea. And yeah, so just hit this thing because it's got a lot of stuff, conceptual. visual coordinate tools or whatever. So here's my De Moivre random variable, and just 20 samples from it. And then I am simply going to sort it and plot it. So this is my empirical distribution function for it, right? And then the question is, this empirical distribution function is going to be my estimate of the De Moivre random variable. You know, because for finitely many points, the De Moivre random variable is the ultimate thing. Because if the thetas are arbitrary, I just need like k numbers that sum to 1. So it's a point in the simplex. So for finite discrete experiments, that's a point in the unit simplex. So and then the empirical distribution function is directly hunting that point. Is the idea. For continuous ones, it's more complicated, right? Okay, here is the Glivenko-Cantelli theorem. It says that if my x1 through xn is ID according to some unknown f star, then the empirical distribution function has this interesting convergence and probability. So the supremum means essentially the maximum of all the x's downstairs, where the absolute deviation between fn, the estimate, and the unknown, whatever it is, converts in probability to 0. It's a pretty crazy statement, right? It's saying no matter what. So I'm looking at this is in absolute deviation. So I'm looking at find me the x where the jump fn hat, this jumpy thing, empirical mass function, is farthest away from the unknown thing f star. Okay, that's what this is saying. So this is exactly where it's farthest away, and that maximal deviation converges in probability to 0. That's what the Glivenko-Cantelli theorem says. No matter what the underlying f is. So that's basically what we're doing here. So if in my interact for the De Moivre, if I keep increasing the sample, you will start seeing this is an equiprobable De Moivre by construction, so it's easy to see. It's just converging to the 0.2, 0.2, 0.2 thing because there are 5 faces of this polygonal die or whatever, right? So it's saying that the true distribution will have jumps at 0.2, 1, 2, 3, and 4 of height 0.2 because it's a equidistant die, and that's exactly where the distribution function is going. And this one's just giving me another example. So if I have a uniform density, if I have lots of samples from the uniform, so the blue one is, remember, the distribution function for the uniform, right? It's just this identity function. So if I increase the sample slowly, you see, it's really starting to hug this, right? I mean, now my plots are a bit ugly, right? I'm not making my ball size is small enough with the, but yeah, it's just saying where the maximal deviation of the empirical distribution function from the truth will go to 0 in probability. That's what the theorem is saying intuitively. And then the inequality comes on and says something stronger. It says not only is the maximal deviation going to go to 0 in probability as n increases, but the rate at which it goes to 0 can be really precisely specified. This is super beautiful. So now we're moving into the world of set estimation already. So what this says is the probability that the supremal deviation of the empirical distribution function or point estimate from the truth being more than epsilon is less than or equal to 2 times e to the minus 2n epsilon squared. That's pretty powerful. So you give me any epsilon, however small, close bigger than 0, then I have this inequality satisfied. Okay, so that's some more like I don't know, it's an information bound or whatever. It's just a inequality. So this nice thing allows me to produce confidence bands C sub n of x. So now I have a lower band and an upper band that, and then the point estimate itself, fn hat. And these lower and upper bands, because of that inequality, are guaranteed to trap the true distribution function with a very high probability. That's what this becomes. So now I have tubes trapping the unknown distribution function from above and below with a very high probability. So that's essentially, these are all just how to get this epsilon n padding from the theorem thing. So it's no biggie really. Just look at some pictures quickly. So I've got to sort them, right, because this is the empirical distribution function. And yeah, I'm just basically doing Kim-sum and then relative frequencies, and finally zipping, so sort of looking through the. So here we go. So there is a. This is my empirical distribution function for some simulation. Now I can do my epsilon calculation like this. Okay, so I want with probability 95%, so I put alpha as 5%, 0.05, and it gives me this little calculation that I need to pad my point estimate by. And so if we can, to get the lower bound, we just have to take the maximum of the point estimate, which is, now the point estimate is the empirical distribution function because we're estimating points in this set of distribution functions, right? And then I subtract epsilon n, and I take that or 0, the maximum of those two. So that way we don't go below 0, right? So that's the lower band we can get out of that inequality by thermal fluids. And then we can get the upper band, Cn super of x, by doing just plus epsilon n, and the minimum of that n1, because we don't want the distribution function to be ever above 1. So these inequalities are just coming directly out of the theorem. So then we can get the heights for the lower band like this by just putting in this this exact formula, and then we can do these zippings, and voila, we have now the lower band. You see the green lower band? It's, well, the sample size is so small, so it's there. And one of your UTRA exercises is to write the upper band. I don't think I put the solution there, I hope. So yeah, you try and do the same thing to put the upper band, because you really want to go through this a bit slowly on your own. So then you'll have a green lower band and a green upper band that is, with a 95% chance is likely to contain the full distribution function. So that's what, when you're done with it, you'll see a green lower and a green upper. And you can send me the Jupyter notebook with your name on the top, so that way I can keep track of the assignments. We don't have to physically meet if you don't want to. Okay, so I'm almost done. Yeah, so now we are, so we have 12 more minutes. So this is plenty of time. Let's go into the earthquake. So I just wanted to, remember we did all this hard work already and wrapped it into a function. So I'm going to basically call my earthquake file and get my inter-earthquake time in one little cell. And now I have my inter-earthquake times already. So what I want to do is to, so here I can just, see, this is what, someone was asking, you were asking, right? Why should I limit myself to the exponential distribution for inter-earthquake time? Well, you don't have to. So here's the thing, right? So you can get the distribution function, the empirical distribution function as the point estimate, which is this gray one. And then using the inequality, we can get the lower and upper bands for it. And in fact, this is minimally how earthquake engineers and anywhere in New Zealand, for example, will build their concrete beams to be guaranteed for the next 300 years or whatever, because the city budgets will be based on, simple things like this, right? Because you know how probable a certain kind of, you can do the same on magnitudes, for example, right? Which is a nice exercise to try. That's one of the other fields. So then you know the empirical distribution function for magnitudes. So then you can ask with some probability, what are these high probability events, and actually get the confidence interval for the probability. Because if you slash it this way, what is that? So I want to know, it just gives you an interval back downstairs. And so you can do very simple things directly with nonparametric information, nonparametric estimates. Okay, so hypothesis testing is the other main thing. I just want to briefly mention in the last few minutes, and then go to the colloquium. So hypothesis testing is basically like this. So you have some kind of true state of nature, and H0 is the null hypothesis. So remember, because of Popper's falsifiability, the scientist or your sort of colleague is trying to show that you're false, or you yourself are. So the possibilities are the null hypothesis is true, the null hypothesis is false, and so when whether you reject the null hypothesis or you don't, and then these have these type 1 and type 2 errors, right? And basically, these are sort of some, this thing called the p-value. which is essentially one way to conduct a hypothesis test. This is the so-called frequentist way of doing it. The scale of evidence against the null hypothesis is usually stated in terms of the p-value. It has a precise meaning, you know. So this is the interpretation of the p-value anyway. If the p-value is really small, then there's very strong evidence against the null hypothesis. And if it's like between 0.1 and 1, there's little or no evidence against the null hypothesis, right? So, yeah, I mean, don't worry too much about all the meanings, but the main thing I wanted to give you is a flavor of permutation testing. So, for example, for parametric hypothesis testing, you guys already have everything, pretty much. I haven't worked it out. But remember, you have the central limit theorem. So this is the basic recipe for parameter hypothesis testing. Because of central limit theorem, you have your point estimator, right? And the point estimator has some Gaussian distribution when n is large enough. So then you say, oh, I'll look at the outer quantiles of this normal. This gives me my confidence interval. So you'll call this theta sub n hat subscript. I don't know what the normal notation is. And then this is theta sub n hat superscript. So this gives you the interval. So then the idea is you will have your null hypothesis where you will say, I conjecture that my null hypothesis, usually put a theta naught instead of star. My theta naught is 0.8, whatever you usually say. Or it's a fair coin, let's say, for the Bernoulli. I surmise my coin is fair. Then you do your experiments. Your theta hat comes to be something. But you will take this whole confidence interval with a 95% chance. So then, essentially, what you're trying to do is, if this half is contained in this interval, then you cannot reject the null hypothesis, basically, right? So this is called the Wall test, right? So this Wall is the guy from the 40s. Actually, Wall died in a air crash right above the city I was born in. It's completely coincidence in the 40s. But all the stuff we're doing is Wall's decision theory. Yeah, I think he was coming to visit St. Thomas Mount because one of the first Christian monasteries was built in my hometown long before Christianity ever reached Europe. It's a long, spice, great story. So anyway, but he piloted his own plane apparently. So anyway, that's so permutation testing is this other idea. So now that's parametric. So everything basically plays off of what we've learned, right? You just have to read a bit more Wikipedia. Permutation testing is this other world where now we want to do non-parametric and exact hypothesis testing, right? That's parametric. So here the main idea is you are really not the same idea as before. So you'll suppose we have two samples, right? X1 through Xm and Xm plus 1 through Xm plus n, right? Just have two set of samples. And our model is that the first m guys are IID according to an F star, some distribution, arbitrary distribution F star, we don't know. And then the remaining guys, are IID according to G star. This is so-called A/B testing these days in data science, right? So you will have customers that are fed certain kinds of feeds through their, clicks or whatever, the images they'll be shown. And then and then there'll be another set of customers that are given a different kind of feed, movie recommendation, whatever, different parameters in your recommender engines, whatever you do. Then you want to know if there's actually a difference in the behavior of this set of customers and this set of customers, right? That's called A/B testing. It's exactly the same. It uses the same ideas. So if you read the data8.org course, remember this is the course that's recommended, DS8, the first semester freshman course. They give you all these examples from that world. So here the hypothesis testing problem is this. The null hypothesis is F star equals to G star. And then the alternative hypothesis is that F star is not equal to G star, right? So this is kind of interesting, right? So we're now saying we have two things that live in the space of all possible distributions, possibly. So that's what I'm interested in testing. Are the two unknown distributions from these two samples the same or not? And to do that, it's actually not that complicated. So I won't go into all the mechanics of it. But the basic idea is that you have to have the intuition to come up with a basic test statistic, right? This is the statistic designed for the test. So what do we do in a test statistic? One simple thing could be, maybe you're giving two different group of people some food or whatever, not people say rats, different feed. And then you want to know how long its tail is, for example, right? And you want to get long-tailed rats. So then you can do just the mean of the tails of this group of rats and this group of rats, for example, or how heavy they are, right? So feedstock or whatever. So then this is a natural test statistic. I mentioned the absolute difference in the mean of some measurement from each group, right? And I want to know if there is a significant difference in this statistic, right? Because if the two groups are different, then this value should be, should be big, because if there is a difference in the mean of the two groups, then t will get big. So that's usually how you set up a test statistic. So then the idea is basically very simple. You will take all your data, x1 through xm plus n, right? That's what you observe. And then what you're going to do is you're going to permute it. So there's going to be, m plus n factorial permutations. So we'll use this Monte Carlo pseudo-random numbers to sample, right, from this large m plus n many samples. You would sample permutations of them. So if the null hypothesis were true, then the permutation should not matter, because under the null hypothesis, f star and g star are the same, right? The two samples have the same distribution. So permuting should not change. Permuting should not change anything under the null. So that's called the sampling distribution, or the null distribution. So of course you cannot look at all m plus n, the whole factorial possible permutations, because there are too many of them probably. So then you just sample from them. And then your sort of central limit theorems and all of this will guarantee that if the number of samples is large enough, you are going to basically simulate now the sampling distribution or the null distribution of the test statistic t. And then the idea is exactly the same. You ask, of all my simulations of the test statistic t, right? Because once I permute it, I still pretend that my first m are from the first population and the last n are from the second population. And then I do the absolute difference. So I repeat this test statistic over and over for every permutation, say 1,000,000 times, and I'm going to get 1,000,000 test statistics, which is going to have its own distribution, right? Some kind of a distribution. So then you ask, say my observed test statistic is really in the tail. This is my p observed. Then it tells you that the probability of observing this under the null is so small. That's basically the p-value. So the p-value will be the fraction of simulations, fraction of permutations, where this where the simulated test statistic is larger than the observed test statistic. Because the larger means more significant, right? Deviation from null. That's how we set it up. Because if the two rats have the same underlying distribution, the tails won't, So it depends on how you set the test statistic up. And that's exactly what all of this is explaining, and that's basically behind A/B testing these days, right? Okay, and I will stop here in the next 2 minutes. Mechanics, right? So this course is done. So each of these courses are 1 HP for 1 day. So this, if you came to at least 2 of the lectures, then attendance is satisfied. And for this one, for example, a good assignment will be, finishing that upper bound, going through and understanding it too. But and I think some of you already did the assignment for the last module, which is doing a simple random walk in 2D and in 3D if you can. Yeah, I don't remember, there was another U tribe earlier, right? So just do at least one. I mean, as I said, you're supposed to put several tens of hours per day of teaching, because every HP is about, yeah, anyway, I don't care. It's your government. Getting the money out. So anyway, but I still have to grade you, and so if you send me these notebooks, then I can archive them, so I can report to whoever needs the grades or evidence for the grades. Yeah, there's no assignment really for the first day, because that was like a lot of stuff. Are there any other questions?
Why do you do something with that?
Well, I mean, so basically the only logistical issue, honestly, is because if you're going to email me, and also remember, if you guys have done the social media module or the one, the geospatial one, or the Spark one, you're supposed to have done something, right? Those you can hit the publish button and put your name and maybe a link to the course, the 360 specific course. And then you can share the link, the published link, with me directly. So a lot of people have done that. That way we don't have to meet physically. Not that I don't want to meet you guys. I love you guys. I have a life. So that would be very simple for those two courses, right? Or those 360 series. Sorry, the Apache Spark Databricks based one. For this, I think the simplest would be just email me the particular notebook with the, with one of the try assignment things, and then I can archive easily. And the deadline, the problem is the person that collates all of this and sends it to all the departments, she likes to do it in one go. So if one person is not going to give it until July, that's going to like basically cascade, and I really don't want to send it to many times to her, and it's not a. So that's the thing. So we should set ourselves a reasonable deadline. And I said June 4th because but I'm happy to maybe June 10th. You said your exams.
Yeah, that would be perfect.
So should we say June 10th? Is everyone okay with that?
I won't be back until 17th.
Well, for you, we'll make a special exception, But I don't want to overly push it because.
Perfect.
What do you think, Lee? Is that you would like it to be like till December, wouldn't you? Yeah. No, I mean, and also these guys are too. So, because this is the first time we're trying to do this with certifications and all. I mean, it's a certificate from the department, nothing more.
Yeah.
So it'll be nice to do it all before people go on vacation. So let's say June 17th is the absolute latest. So you land here on June 17th? Or?
Yeah.
Oh man. So let's see. Let's really fix a date. But it's just from within Europe, right?
No, it's from the States.
Ah, man, I can fly from New Zealand all the way to Siberia, non-stop. Then it's crazy to give a talk to a bunch of Russians. Okay, let's say June 18th. Okay, Monday, June 18th is like absolute deadline for everything. And then, okay, so let's go to the colloquium, guys. Please go. I'll follow you. I know you may not understand everything, but it's really worthwhile going because you're now immediately seeing the absolute cutting edge of math stats. So, it's technically part of this sequence, so that's why I kind of went in a hurry. So just go to the colloquium room. It's down the hall. And there should be coffee or something there.
Ja, och det gjorde det. Ja, kul.
Men sen ska jag bara göra det till
Jag har en uppställning som jag tror på. Så det var
Och ingen tror på.
Jag får se vad jag ska nå.